So yes, I'm Simon Apers. Thanks for the introduction. Thanks for organizing. To Alex and Fred, I'm super happy to be here and see people. It's a very nice experience. I'll be talking about the quantum complexity of minimum cut. Feel free to interrupt at any point. So there's going to be a lot of computer science and graph theory and so on. And I think it's important, like if something is not clear, to just interrupt me. There's no worries in that. This is a joint work with Ronald de Wolf, Troy Lee, and Pavel Garvichowski. So I'll start with some dry material. A graph G consists of a set of vertices V, or nodes, which are denoted as circles here, a set of edges E, which are basically unordered pairs of vertices, and every edge has a non-negative weight, W. Okay? The number of vertices are denoted by N, and the number of edges by M, which is at most N choose 2. Okay? So a cut in a graph G is equal to a subset of the edges, so that if we remove this subset from the graph, so we do it by G minus C, then the graph becomes disconnected. So basically we're assuming that the input graph is always connected, and so in this case it's just like a subset that disconnects the graph. Like this subset of red edges, we disconnect the graph. A minimum cut, or at least the value of a minimum cut, is equal to the weight of the cut with the least total weight. So what's the weight of a cut? The weight of a cut is equal to the weight of the total weight of the edges involved in the minimum cut, in the cut. And the value of a minimum cut is basically the minimum weight of a cut. We can equivalently, so mathematically it's defined as follows, basically just this minimization. Equivalently, we can define it as a minimization problem over bipartitions, where we take a subset S and its complement, and we want to minimize the number of, or the weight of edges that cross this bipartition. That's what we call a minimum cut, and the value of this cut is the minimum cut value. So this is a very fundamental problem, I'm sure most of you have heard about it in both graph theory and combinatorial optimization. This problem is relevant for studying the robustness of a graph, like in the sort of communication network, but it's also very useful in graph partitioning, like if you want to do divide and conquer, or in designing integrated chips, like we're doing here. Some related problems that you're also probably familiar with, or potentially familiar with, are maximum flow, minimum K cut, where we're interested in sort of the minimum K partition, not the 2 partition, minimum ST cut, where we want to separate 2 vertices, sparsest cut, and so on and so on. So it's really a whole class of problems. And there's a very long line of research that studies this minimum cut problem. It started in the 1970s by the first polynomial algorithm by Podor-Hugin, and it went on through the 90s, so through a long sequence of works. The classical complexity of solving this problem was brought down to near linear, which is almost optimal classically, so O tilde M, where M is basically the size of the graph. This was a very important work by Karger. And actually this goes on till today, because there's well, I mean, not literally today, but let's say a couple of months ago, there was this big breakthrough by Jason Lee, who proved the first deterministic minimum cut algorithm in almost linear time. So basically he sort of de-randomized this algorithm by Karger, which was a long-standing open question. What do we do in this work? This work we characterize the quantum complexity of minimum cut. So what does that mean? It means what is the complexity of solving a minimum cut on a quantum computer? Again, what is complexity? I'll be approaching this from 2 angles. One of them is query complexity. When we talk about the quantum query complexity of a problem, we mean if we have query access to the input, what's the total number of quantum queries that a quantum algorithm has to make to this input to basically determine or solve this problem. While the query complexity is often trivial for classical algorithms, like for instance for a minimum cut, it's not hard to show that any classical algorithm should basically see the full set of edges before it can decide what the minimum cut is. Often quantum algorithms can solve problems in sublinear time. A simple example here is if we can make queries to some input string x, which has a capital N bits, we want to determine OR of x, which is basically the question, does there exist a single 1 in x? Then classically we need to examine the entire string, whereas quantumly we can use Grover search to just find a single 1, which takes order of square root n quantum queries. So this concept of query complexity is a very important one, and makes a lot of sense to study it from the quantum perspective. Now, what's the quantum query complexity of a graph problem? So again, we want to make queries to the input. Now, unfortunately, there's two kind of models that make sense here. So this is going to obfuscate a little bit my exposition, but let's try to bear with me. On one hand, you can describe a graph as a adjacency matrix, which is basically an n by n matrix, where entry ij captures the weight of the edge between I and j. And if there's no edge, we would give it weight 0. So the input size here is n squared, irrespective of the number of edges. And the query takes the following form. We just give as input of vertices I and j, and we get back the weight of the edge between I and j. Then there's the second model, like I mentioned before, also classically, when we talk about a graph, typically the input size of a graph, or the description size of a graph, scales with m, the number of edges. And this is basically what we mean when we talk about an adjacency list of G. So basically, we think that every vertex carries a list of all its neighbors and the weights of the corresponding edges. So the total size of this list is scales with m, the input size. So for a sparse graph, we would have a smaller input size. And our query takes a slightly more complicated form. Basically, we have a vertex I and an index k, and provided I has at least k neighbors, we return the index of the kth neighbor of I and the weight of the corresponding edge. So we're basically just querying for the kth entry in this list of a vertex. That was quantum query complexity. I'll also be talking about quantum time complexity, which is basically sort of how hard will it in the end be to really solve this problem. Like how large will the quantum circuit be for solving this problem? More specifically, we'll be describing quantum algorithms in sort of circuit model, and the time complexity of the algorithm measures the total number of elementary gates, but also queries to the input graph, and also QRAM operations. So I'll just mention a little bit here that often in these sort of graph type problems, we need to assume sort of memory that we can store, which doesn't quite fit into this circuit model, unfortunately. It's like an extra assumption. So what we're assuming is that we have this extra memory where we can classically modify the memory, like update bits or put information to this memory efficiently, and quantumly we can just make coherent queries to this memory. It's a bit like the type of queries that we can do to the input. We assume that we can also make these queries to this RAM memory. Okay. So why should we study the quantum complexity of graph problems and problems like minimum cut? They form potential long-term applications, right? So again, minimum cut is a very important problem. It's also used to solve other problems. And so it would be interesting if we could use quantum computers to solve this problem faster. It also gives a better understanding of limits and opportunities of quantum computing. Then, and this to me is also very important, motivation is that often thinking about the quantum setting gives new insights in classical algorithms as well. In that sense, the quantum setting is a bit similar to say, other settings like the streaming setting, dynamic setting, distributed algorithms, deterministic algorithms, and so on, where basically you look at a very canonical problem like minimum cut from a new perspective, potentially with new limitations, but with other sort of new things that you can do. So the same holds for a quantum setting, and there's many examples where we actually get new insights into classical algorithms by using this sort of quantum lens. And finally, a slightly more esoteric motivation is that if one argues that in some sense quantum computation is more fundamental than, or at least quantum mechanics is more fundamental than classical mechanics, then quantum computers are more fundamental than classical computers. And so if in some sense we want to characterize the true complexity of a problem, then this would be a reason to look at the quantum complexity of a problem. Then I'll just mention this recent very nice survey talk by Ronald Wolf at Simons Institute on quantum algorithms for optimization, which touches on a lot of this material. Now, I already mentioned some common caveats which arise when you talk about quantum algorithms and graph problems, at least the types of quantum algorithms that I'll be talking about. One of them is that the types of speedups that we can get are typically polynomial and often even subquadratic. So I already mentioned this Grover type speedup that we can get for evaluating the OR function, which is a quadratic speedup. Now, in many problems, we actually get even just a subquadratic speedup. And the second one is this QRAM requirements. Okay, so let me talk about some examples other than minimum cut where the quantum complexity was studied. One of them is, and this is a very profound example is a triangle finding in a graph. So basically, we're given an input graph. Now we'll assume that the graph is given as a matrix, so we're in this adjacency matrix model, and we want to find a triple so that basically there's vertices between every pair of vertices. So it's like a 3-clique. Using Grover search, naively you can just solve this problem in O n to the 1.5 by searching over the set of triples of vertices. By being a bit more clever, you can bring this down to n to the 1.428. And then by bringing like just a whole range of new tools like quantum walks, learning graphs, and so on, you can further bring this down to n to the 1.3, n to the 1.296, 285, and eventually n to the 1.25 in 14 by Legal. But this still leaves a big gap with the best lower bound that we have, which is omega n. And so I'm mentioning this problem also because this is a graph theoretic problem that's related to a potentially even more profound application of, namely, element distinctness. And also this very nice example where new improvements on these query bounds often go paired with new tools in quantum query complexity and new insights. Then the second problem is, given an input graph, is this graph connected or not? Notice that this problem is, in some sense, an easier problem than minimum cut, because what we could do is on this graph, we could solve for the minimum cut, and if the minimum cut is 0, then the graph is unconnected. If the minimum cut is larger than 0, then the graph is connected. Now, this problem was studied in 2006 by Dürr, Heiligman, Hoare, and Mala, where they showed that the quantum complexity of solving this problem is scales as n to the 3 over 2 in the matrix model, and scales with n in the list model. So again, we see that in this list model, because we have this sparse representation, often we can do things better than in this matrix model. And notice by my former argument that since we can use minimum cut to solve connectivity, the corresponding lower bounds give us the same lower bounds for a minimum cut. The upper bounds do not carry over, obviously, because just determining whether a graph is connected does not tell us what the minimum cut is or what its value is. But we do get these lower bounds, and this already limits kind of the scope or the range of speedups that we can hope for. So building a bit further on this types of lower bounds and so on, let me give some intuition, some quantum query bounds for this problem of minimum cut. So we already saw one sort of query complexity problem, which is evaluating the OR function of an input x. Here we consider a slightly different one. We're given an n by n matrix, a Boolean matrix, a 0-1 matrix, and we want to determine the number of ones in this matrix, or basically the Hamming weight of the matrix X. Now, this problem has long been known. This basically follows from a result by Beals, Burman, Cleave, Moska, and de Wolf, that this problem of counting, because that's basically what we're doing, we're evaluating the Hamming weight of this input, requires a number of quantum queries that scales with the size of the graph. So basically, even though we have Grover search and we have all these sort of quantum speedups, we cannot get a quantum speedup for counting, because basically the quantum number of quantum queries that we have to make scales with the size of the input, which is the same as classically. So we cannot get a quantum speedup for counting. Now notice that we can use this insight to say something about minimum cut. Consider the following graph, where we have two sets of vertices, left vertices and right vertices, and we build up the graph as follows. Between every pair of vertices on the left side, we put an edge with weight alpha, where alpha is a very large integer. And between every pair of vertices I on the left and j on the right, we put an edge only if and only if entry xij is equal to 1. So basically what we're doing is we're encoding this matrix from the last slide into the adjacency matrix of this larger matrix, which now takes the form, we have basically this block structure where the diagonal blocks correspond to these heavy cliques here, and these off-diagonal blocks are basically the encoded matrix. Now notice that a minimum cut in this graph will never cut any of these, like it basically will never separate vertices on the left or on the right, provided alpha is sufficiently large, because we would always need to cut some edge with weight alpha, and assuming that alpha is very large, we will never want to do that. And so we can basically enforce that the only minimum cut of this graph is exactly the one that crosses through the middle. Now, what's the value of this minimum cut? The value of this minimum cut, again, is the total weight of edges that we cross. In this case, would be exactly equal to the Hamming weight of x. And so what we see is that we can reduce the problem of counting to that of minimum cut. So exactly evaluating the minimum cut in a general weighted graph, we can't do this faster than classically, basically because we can encode this counting problem in there. And this idea, I mean, it really shows up in many sort of graph problems where ideally we would like to do something quantumly sublinearly, but if you want to go sublinear, because of a sort of counting lower bound, we can only afford an approximation, for instance. Now here I'll show that the story is slightly more interesting. Namely, there's this one loophole which I just mentioned, which is that if we only want to epsilon approximate the Hamming weight of x, then we actually can get a quantum speedup. This is this quantum counting algorithm by Brassard, Hoyer, Mosca, and Tapp. And this provides a way of circumventing this counting lower bound. So it raises the question, can we get a quantum speedup for approximate minimum cut rather than exact minimum cut? And then there's the second sort of small counting loophole, where we can get a quantum speedup for exact counting, provided that the Hamming weight of x is small. And this is closely related to the Grover search speedup that I've already mentioned, which is that if the size, the Hamming weight, or the number of ones at most k, then we can just use Grover search to find these k ones in this n by n matrix, which requires a number of queries which scales as square root n squared times k. And so if k is not too large, then we actually get something which is smaller than n squared, and so we do get a quantum speedup. So this raises the question, can we get a quantum speedup for minimum cut if there are not many edges involved in the minimum cut? And this seems like a bit of a not particularly interesting question, but it turns out that actually it is. So let me first talk a bit about this first loophole, which is approximate counting. And I'll do so by demonstrating that indeed for approximate minimum cut, we can find a quantum speedup. So this is based on joint work with Ronald de Wolf. So the key idea, again, is to exploit this approximate counting loophole. And I'll explain the algorithm by first showing how we can get a quantum speedup for constructing a so-called graph sparsifier, which I'll explain in a second, and then just solving minimum cut on this sparsifier of the input. So what's a graph sparsifier? Slightly more specifically, a cut sparsifier of an input graph G is a subgraph which is potentially reweighted. So I'm putting some edges thicker here because we're taking a subgraph, but potentially we're increasing the weight of certain edges, so that H is sparse, which is kind of the whole idea of sparsification. And every cut in H, so if you take a subset S, we look at the weight of edges that cross this cut, should epsilon approximate the weights in the original graph. And this should hold for every subset S. In particular, this implies that the minimum cut of H should epsilon approximate the minimum cut of G. Now, this seems like a very nicely useful concept, the sparsifier, but can we actually get a sparser subgraph that approximately preserves all the minimum cuts, sorry, all the cuts seen? So this was most famously shown by Karger and Benser-Karger, that basically every weighted graph has an epsilon cut sparsifier with only O tilde n over epsilon squared edges. So if I didn't mention, I'm hiding polylogarithmic factors with this tilde here. So if epsilon is constant, then this is a number of edges that's near linear in the number of vertices, which is almost a quadratically fewer amount than basically the possible number of edges, which scales with n squared. And moreover, we can actually find this sparsifier in near linear time, so very efficiently classically. This is a building block of many classical approximation algorithms for graph problems, and it's a crucial component in efficient classical algorithms for exact minimum cut as well. So you're working with this approximation, but in the end, you can still use this sort of approximate cut sparsifier to actually solve the exact minimum cut problem. But this is not so easy. What did we show? We showed that there is a quantum algorithm that, given let's say adjacency list access to this input G, constructs an epsilon cut sparsifier in a number of queries that scales with square root mn over epsilon. So this is sublinear. Let's assume for a second epsilon is constant, and if the input graph is dense, so m scales with n squared, then we get a speedup from n squared classically to n to the 3 over 2 quantumly. So this is also what I mean by these sort of subquadratic speedups that you can get. because what we showed is also optimal, so you cannot get a larger speedup than this n squared to n to the 3 over 2. But nevertheless, it's a useful speedup, and at least from our theoretical computer science perspective. And I'll just briefly sketch how this algorithm works. So we start from this classical idea of iterative sparsification, where we're given some input graph G, and this input graph G has potentially many edges. Like, let's say we have 2 cliques connected by a single edge. Then we feel that, whereas this edge is a very important one, the edges inside the clique are somewhat redundant. Like, if we would lose a single edge there, we wouldn't care too much. And so what this iterative sparsification algorithm does is, first it constructs a small set of spanning trees in the graph, which I'm indicating, like, for instance, in red here, this is a spanning tree. And notice that any spanning tree should contain this edge here. So we basically use these spanning trees to identify what are the important edges in our graph. And after doing that, we can kind of safely say that the remaining edges are somewhat redundant. And so what we can do is we can downsample the remaining edges with probability 1/2. So we just keep a random half of the remaining edges. By doing this logarithmic number of times, we end up with a graph which has approximately n over epsilon squared edges. And this will in fact be an epsilon cut sparsifier of the input graph. So how does the quantum algorithm approach this problem? We basically use a quantum algorithm to find these minimum spanning trees faster, which is something that's not all too hard to do. And then one thing we can do quantumly, so classically you can just iterate over a full set of edges and just toss a coin for every edge and just remove an edge when you don't want to keep it. But quantumly you want to do things in sublinear time, so we have to kind of implicitly sample these edges. So this takes a bit more work. Again, repeating this order log n times, you get this epsilon cut sparsifier. And this gives us this total complexity after, again, after more work of Otilla square root mn over epsilon, which is optimal. So there's also an omega square root mn over epsilon lower bound that we prove. This gives us the following very easy speed up for approximating minimum cut. Once we have a sparsifier, namely, we can just construct this epsilon sparsifier. This takes Otilla square root mn over epsilon queries, or time complexity. And now we have this sparsifier h, but notice that the sparsifier h, we now have it written down on a piece of paper. We don't make any more queries. Now we're just going to solve this minimum cut problem on this graph h. So we don't care about the input graph anymore. We just care about h. So we're not making any more queries. We're just solving this classically. So if you just care about query complexity, you can just run any algorithm on this sparser subgraph and solve for minimum cut. If you do care about time complexity, then notice that this graph is an easier instance than this one, because this graph only has Otilda n edges, and classically we can solve minimum cut in near linear time. So solving minimum cut on this graph just takes Otilda n time. So this gives us a Otilda square root mn over epsilon time or query algorithm, quantum query algorithm, which is basically what this theorem states. Using a similar idea, and using rather than a cut sparsifier, a slightly stronger concept called a spectral sparsifier, we show that similarly you can approximately solve other cut problems, but also approximately solve Laplacian systems and so on. But I'm not going to go into the details of that. And obviously there's this open question, whereas we show that Otilda square root mn over epsilon is optimal for constructing a sparsifier. Nobody really cares about the sparsifier. You just care about the things that you can do with it. So what we'd like to prove is that, for instance, epsilon approximating the minimum cut should also require that many queries. But this is something that we've tried pretty hard, but we don't manage to prove any sort of non-trivial lower bounds here. So I think that was it for approximate minimum cut. Yeah. Oh, sorry. Yeah, this is a JCC list model. So you can always think like.
Oh, because the other one you cannot.
In the other one, you actually. Any algorithm in a JCC list model, you can basically see you can complete the list with all zeros, so it basically becomes a matrix. But then the m becomes n squared, and so basically you can always replace the square root mn by n to the 3 over 2, which is like the JCC matrix complexity. So you get the same type of speed up for the JCC matrix model as well, but again, it's an approximate. We're just approximating the minimum cut, so there we can get a speed up. So this was exploring this one loophole. But I mentioned there's a second loophole, which we'll exploit in this joint work with Choi Lee, where we construct a quantum algorithm for exact minimum cut, but for simple graphs. So again, we're exploiting the small counting loophole here. And what we're using is that in simple graphs, the number of edges that are involved in minimum cuts is small, is necessarily small. And this is exactly what you can exploit with this small counting loophole, right? If you want to count, but the number of elements that you want to count is small, then we actually can get a quantum speedup, even for exact counting. And then we'll use these edges. We find these edges using these graph sparsification ideas. So this is really like a follow-up work to the previous work. Let me first focus on just the query complexity, because the time complexity is kind of a more complicated story in this problem. So I mentioned that simple graphs have a small number of edges involved in the minimum cuts. And this was an observation by Kawarabayashi and Thorpe, a pretty profound observation that in the end is not all too hard to prove. Like there's a self-contained proof, just half a page. But the idea, let me sketch the idea. This is the graph that we saw before, where we have this clique here, and then we just have this sort of set of edges here in between. And if we take alpha to be very large, then we can enforce the minimum cut to cross through the middle, and so the number of edges involved in the minimum cut can be as large as n squared. But if instead we enforce alpha to be equal to 1, this is what we call a simple graph, namely a graph where all, it's basically an unweighted graph, so all edges have weight 1, then we get that, for instance, if we look at this trivial cut here, where we just cut off a single vertex, then the value of this cut is at most n minus 1, because this vertex can only have an edge going to each of the n minus 1 neighbors. And since all edges have weight 1, this gives a cut value of n minus 1. Now, if this is the case, then if we still want that the min cut goes through the middle, then we cannot put more than n minus 1 edges through the middle. And so we see that by taking alpha to be 1, we cannot enforce basically the minimum cut to cut through a lot of edges. We can only cut through n minus 1 edges. And that basically proves that any minimum cut has size at most n minus 1. So that's a very simple observation. But the harder observation by Kawarabayashi and Thorpe was that actually if you look at the full set of minimum cuts, because the graph can have more than one minimum cut, this full set still only involves at most order n edges. So somewhat more specifically, what they proved is that if we have a simple graph, then there exists a partition of the vertices into components P1 until up to Pk, so that if we ignore the edges inside the partition, but only look at the edges between the partitions, then there are only order of n edges between the partitions. And secondly, any minimum cut, so this is actually only holds for non-trivial minimum cuts, where a non-trivial minimum cut is one that does not just cut off a single vertex. Like if you cut off at least 2 vertices, so basically these are sort of cuts that are not trivial, like this cut here. If we, basically every near minimum cut that's non-trivial will go between these partitions. So basically the only edges that are involved in non-trivial minimum cuts are those between the partitions, and there's only order n of them. So that's what they prove.
What do you put in a simple graph?
Unweighted. Yeah. So okay, in principle it's unweighted, and there can be there cannot be like multiple edges between 2 vertices. It would be a multi-graph. But I wanted to avoid that because there's going to be some multi-graphs later on. But yeah, it's a good question. Thanks.
And no self-loops.
No self-loops. Yeah. But I guess they wouldn't matter for cut problems because you can't cut through a vertex. Yeah. So this holds for simple graphs. What we did in our paper, maybe just to elaborate a little bit on this, we showed that for weighted graphs, if the weights are between like 1 and tau, then actually the number of edges is at most tau times n. And so if the weights vary wildly, like if there's weights of value n and value 1, then you can actually get that all edges are involved pretty much. But if it's somewhere in between, then we should actually get a result which is also in between. So this gives a relatively simple quantum query algorithm where I'm going to put something under the rug, namely, let's assume that we have this KT partition. Like we have this vertex partition, which I'm describing it just takes basically scales with n, right? We just have to describe this partition of n vertices. If you have this KT partition, then what we can do now is we can search over the full set of edges and mark those edges for which the endpoints are between different partitions. Because again, what we would like to do is ignore all these edges inside the partitions and only look at the edges between the partitions, which is a very small subset. And so using Grover search, we can actually find these order n edges. And so in an adjacency matrix model, we basically look for n edges among the n squared entries of the adjacency matrix, so we get something that scales with n to the 3 over 2. In the adjacency list model, we have m entries, and we just want to find these n edges, so we get square root mn. So we can find these edges, and once we found these edges, we can do the following, namely, we can just contract these sets, because we'll never cut through these sets. So the minimum cut doesn't care about these sets, so what we can do, we can basically contract these sets, and then we get a new graph, which is now a multigraph. That's why I mentioned before. Namely, between this set and this set, there could be something like 3 edges. Like, okay, it's actually 4, I see, but let's say it's 3. Then we just get a sort of multigraph here, where there's 3 edges between these 2 vertices, 2 edges between this vertex, and so on. And if we now solve minimum cut on this contracted graph, then we're basically finding the minimum cut that respects this partition. And we know that the minimum cut of the original graph respects this partition, so we would find A or D minimum cut of the original graph. And since we're just talking about queries right now, this does not require any queries, because we have this graph written down on a piece of paper. We don't make any more queries to the original input graph. We just have this partition. We learn the important edges. We don't care about all the other edges, and so we make no more queries. So this gives a algorithm that has a query complexity n to the 3 over 2, or square root mn, up to this KT partition that we have to find. So how do we find this KT partition? Like, what's the number of queries that we need to find this KT partition? Like, one naive algorithm, or a greedy algorithm, basically goes as follows. Let's just look at all possible bipartitions of the graph, or basically all possible cuts of the graph. Whenever we encounter a cut that's minimum or near minimum, we just slice through the graph along that cut. And we keep on doing that, iterating over all possible cuts. And so in the end, we will have sliced, basically, we will find a partition that's induced by the set of near minimum cuts. But iterating over this and basically would require way too many queries, so this is way too costly, so we have to be a bit smarter here. Now, one thing that you can do is that you can observe that this concept of a sparsifier actually approximately preserves all the cut values in G. Hence, it also preserves all the approximate or the near minimum cuts of G. And so if we construct the KT partition of the sparsifier, then we actually get an approximation which is sufficiently good for our purpose of the original graph G. And so what we can do is we can basically construct this sparsifier H, and again, whereas we only have query access to this original graph, we have explicit access to this graph H in the sense that it's written down. We don't make any more queries, and so we could just run the greedy algorithm on this graph H and find a KT partition that way. So we get a following query algorithm where we construct the sparsifier in step 1. Then we find this KT partition of the sparsifier. Again, this requires no queries. We use Grover search to find this order of n edges that exist between the partitions. And finally, we just solve minimum cut on a contracted graph. Again, this requires no queries. So we get a query algorithm which scales as n to the 3 over 2 or square root mn, depending on the model. So this gives us the following result. In the adjacency matrix model, we get this upper bound of O tilde n to the 3 over 2 for solving exact minimum cut in simple graphs. On the other hand, I already mentioned this lower bound, which holds in the matrix model by Dürr-Heilig-Van-Horen-Mal on connectivity, which implies a lower bound for minimum cut. So we actually get a tight up to polylog factors characterization of the quantum query complexity of minimum cut. In this list model, and I just want to add that in many cases, I think this is a more challenging model, and also it requires more sort of insight, and you have to be a bit smarter about things, which we didn't quite succeed in. So there's still this gap here in this adjacency list model. Namely, we have this upper bound, which scales O tilde square root mn, and we have this lower bound, which is just the connectivity lower bound. So we've been trying to prove lower bounds again here, but this wasn't terribly fruitful so far. So we have this gap here, and this raises the following open question. And I'm going to phrase it like that. Can we bring down the upper bound? Because I think that would be one most interesting, and that's also what I suspect is possible. But it requires, would require many new insights, I think. So that's what I wanted to say about the quantum query complexity. So again, we resolved this question for adjacency matrix model, but there still is a gap in the adjacency list model. Now, this is quantum query complexity, and in the end, what we really care about is the time complexity. Basically, how long does the algorithm run? And this is something that we looked at in follow-up work together with, again, Troy Lee and Pavel Garvichovsky, who's actually, as Daniel mentioned, he's not doing quantum algorithms, but he's mainly doing classical algorithms and classical data structures and so on. But the problem that we're solving here is actually a classical problem in the end. Namely, if you go back a little bit and we look at this minimum cut algorithm in the adjacency, let's say, okay, it's actually in both models, so ignore this. The algorithm constructs a sparsifier. Now, in this paper with Ronald, we proved that we actually get a time-efficient algorithm. So this step is time-efficient. Then this third step is just Grover search, so also time-efficient. And this last step, as I mentioned before, we can just run a classical near-linear time algorithm, which is very efficient, and we just take time until the n. And until the n will always be sublinear to the complexity that we're aiming for. So really, we should focus on this one step of constructing the KT partition of H. So already, as I mentioned before, we start from a simple graph, and we would like to construct the KT partition of the simple graph. The way to approach it, I mean, what we do is we first construct the sparsifier, and now we want to find the KT partition of the sparsifier. But this kind of strikes back a little bit because, in fact, there is an efficient algorithm, an efficient classical algorithm, which was proven in the same paper by Kawarabayashi and Torup, that actually in near linear time, classically you can find the KT partition, but only for simple graphs. And whereas our input graph is simple, we attempt to simplify the problem by looking at the sparsifier. But as I mentioned before, a sparsifier is a reweighted subgraph. And this is intrinsic to a sparsifier. So you can't avoid reweighting. And so we can't use this efficient classical algorithm by Kawarabayashi and Torup because our graph is no longer a simple graph. So what we did in basically the first paper together with Troy, we proved that there's a quantum algorithm that finds this KT partition for weighted graphs in time, which scales as O tilde n to the 3 over 2. This is both in the matrix model and the list model. So this is very satisfactory for the matrix model because it gives a time-efficient algorithm for the matrix model, but not so much for the list model, which again is what I think the more challenging one. So what we do is we put a bit more effort and a bit more help, I guess, from Pavel here. And what we prove is that actually we extend this result by Kawarabayashi and Torup, but using entirely different techniques. We show that there is a classical algorithm for weighted graphs, which is near linear, and it constructs this KT partition. So this is a purely classical algorithm, but by combining it with a quantum sparsification routine, we actually get a faster quantum algorithm as well, which now scales as the O tilde square root mn that we would have liked to have. So what are the key ideas here? One of them is a concept called tree-respecting cuts, and then another is like a sort of generating set for KT partitions. So what is this concept of tree-respecting cuts? Consider a general input graph G, and consider a spanning tree T. What Karger did is he tried to, okay, if you have an input graph G, then let's say that you want to run this greedy algorithm to find a KT partition by just iterating over all possible cuts. Now, there's exponentially many cuts in a graph, so that's kind of unfortunate and very costly. What Karger tried to do here by using this concept of tree-respecting cuts is somehow get a grip on the number of potential near minimum cuts. Namely, what he showed is that, let's say that a cut 2 respects this graph, this spanning tree T, if it cuts at most 2 edges of T. So, okay, we have this input graph G, we have this spanning tree T. If we would take a cut like this, we would include 6 edges of the spanning tree T. This is not a 2 respecting cut. If we take this cut, then we cut exactly, this cut contains exactly 2 edges of T, and so this is what we call a 2 respecting cut. And notice that now, for a given spanning tree T and a given input graph G, there are at most n-1 choose 2 respecting cuts. Because basically, T has n minus 1 edges, right? If a spanning tree has n minus 1 edges, spanning tree of a graph with n vertices. And, okay, this is not exactly right. So every 2 respecting cut of T cuts at most 2 edges. So if you first look at the ones that contain exactly 2 edges, then there's at most n minus 1, choose 2 of them. But then there's also cuts that might, like this one, that might just cut a single edge. So we actually get n minus 1 plus n minus 1 over 2. But still this scales as order n squared, rather than the exponential bound on the total set of cuts in the graph. So you get a bit of a grip here on the set of cuts, but this is only interesting because of the following lemma, which Carter showed. Namely, if you take an appropriately random spanning tree T. So by appropriately random, you have this concept of random spanning trees. It's not that. Basically, what you're doing is you sort of construct a packing of spanning trees, which is some concept I'm not going to go into the details, and then you take a random spanning tree from that packing. But you can do this efficiently. And what Carter showed is if you take a random spanning tree, in that sense, then any near minimum cut will basically respect this spanning tree with large probability. Here, large probability means something like 1 over log n, something like that. So basically, if you take a logarithmic number of these random spanning trees, then every near minimum cut will respect at least one of them. So that means that if we are interested in near minimum cuts, then we can just look at this smaller set of 2 respecting cuts, which scales again with n squared instead of like exponential in the size of the graph. And we know that the minimum cuts will be contained in this much smaller set. So this is an obvious corollary from this lemma. And I'll mention that actually this is a very roundabout way of proving that there is at most O tilde n squared near minimum cuts. But I'm not familiar with a more straightforward way of proving this. Like, this is a very non-trivial statement to prove. There's a different algorithm which uses a different sort of contraction-based algorithm to basically, again, in a roundabout way, prove that there's at most O tilde n squared near minimum cuts. But it's a very nice and non-trivial result. And there's actually a long line of study now that tries to characterize more tightly like how many near minimum cuts there can be in a graph. Maybe I should also just, it's very late to clarify this, but by near minimum cuts, I mean cuts that are almost minimum cuts, so basically that have a value which is, say, 1 plus epsilon times the value of the minimum cut, where epsilon is, I don't know, like 1 over 10, something like that. So this corollary and this lemma gives us a, say, better greedy algorithm for finding this KT partition. Namely, what you can do is you can just iterate over the set of 2 respecting cuts. And whenever you find a near minimum cut, okay, so basically you iterate over the set of 2 respecting cuts, you evaluate the value of the cut. If it's near minimum, then you slice the graph along that partition. You repeat that. And now, again, instead of iterating over all possible exponentially many cuts, you just have to iterate over this small polynomial set of cuts. But this is still too slow for our purpose, okay? Because obviously, we want to have something that scales with this number of edges in the graph rather than n squared, and any approach that follows this line will necessarily scale with n squared. So what we do instead is we notice the following. It's not too hard to prove, and this is rather elementary, that if you have n vertices and you have a set of cuts that always bipartitions the set of n vertices, then this set can, in some sense, it can be a very large set, but in some sense we can generate the same partition by just taking only n bipartitions. Basically, after a long while, if you keep on taking bipartitions, at some point you're not going to slice anymore. You're just going to be going along the partition that you already had. And it's not too hard to prove that. In some sense, we would never need order n squared bipartitions to find a partitioning of n vertices. And it's exactly what we prove, but in a more structured way. Namely, what we prove is that there exists a, what we call a generating set. I think there should be a tilde here, so it's like n log n cuts that induce the KT partition. And namely, these are, more specifically, these are two respecting cuts. So basically, we show that there's a much smaller set, namely a set of only order n bipartitions that give us the partition that we want, like the KT partition, right? So this is what we call a generating set for the KT partition. Now we still have to find these n near minimum cuts, and I'm not going to go into the details of that because it's a little bit involved. But we show how to find such a generating set. First, in O tilde n to the 3 over 2 with a quantum algorithm. That's what we did in this work. And then we improved this in this work with Pavel Gavichowski to near linear classically and O tilde square root m. So again, there should be an L here in the list model quantumly. And once we have the generating set, it's actually not too hard. Basically, using the appropriate data structures, you can efficiently find the resulting partition of this set of cuts. Let me also mention that in principle, if we would just find a generating set of order n cuts, there's not necessarily a way of efficiently describing the set of cuts, right? Because every cut would be a bipartition of the graph, and if this is an arbitrary bipartition, then this would require n bits to describe, and so the description of this generating set would still scale with n squared. But now, because these cuts are two respecting, notice that any two respecting cut, so if you go back to this slide here, basically just requires to identify the two edges that you're cutting. And once you identify these two edges, you just look at basically what's the one side of the tree and like what's the other part of the tree. And so given this tree, for every two respecting cut, we just need to give two edges to identify, or maybe one edge to identify what the bipartition is. So this is also a very important feature of this two respecting framework. So this proves the following theorem, that we can construct this KT partition of a weighted graph in time O tilde m classically, or O tilde square root mn quantumly. Again, it's in the list model. One corollary here is that we bring down the time complexity of all our quantum algorithms for minimum cut down to the query complexity bound. So we provide time-efficient algorithms, namely O tilde n to the 3 over 2 in the matrix model and O tilde square root mn in the list model. Another corollary, which I'll just mention because I see I have a couple of minutes left, is that you can also use this to get a very efficient classical minimum cut algorithm. Basically, what Carger showed some time ago is that you can solve minimum cut in O tilde m, which is near linear. But this O tilde m hides polylog factors, and specifically what his complexity is m times log cubed of n. And in recent work, people have been trying to improve on this. Basically, have been trying to get rid of these log factors and so on. And this results in a recent algorithm which has complexity like m plus n polylog, which for non-sparse graphs is exactly linear in the input size. So that's very efficient. And we basically get a new type of algorithm that does this, which is kind of a nice side result, and also highlights in some sense that also the fact that this algorithm is classical. Basically, by thinking about these quantum algorithms, we actually get new insights and new algorithms for classical problems as well. Like in this case, for constructing this KT partition. So let me summarize a little bit. The quantum time and query complexity of minimum cut is not quite as settled as I would hope, I guess. On the one hand, what is settled is that for general weighted graphs, we know that there's no quantum speedup. But this everybody could have proven. So that's not all too hard. What we showed in this earlier work, this sparsification work, is that if we just care about approximating the minimum cut, then even for weighted graphs, we can get a quantum speedup. Namely, we can go down to n to the 3 over 2 over epsilon in matrix model, or square root mn over epsilon the list model. And again, we would like to prove a lower bound for that. We have a lower bound for sparsification, but not for minimum cut, which is a bit unfortunate. And then in this follow-up work, we prove that if the input graphs are simple, then we can actually improve these approximate algorithms, again, provided that the input graph is simple, to get exact algorithms with the same complexity. The key tools are graph sparsification, more specifically a quantum algorithm for graph sparsification, and this Kawarabayashi-Toro partition of the input graph. And there's just some open questions, namely bringing down this complexity of minimum cut and simple graphs, but also, and this was also, to me, one of the key open questions from this quantum sparsification paper, is I actually would like to conjecture that we can actually also get this O tilde n complexity for sparsification. And again, as I mentioned before, this in the diff model, I think this is a much more involved and more intricate question than the things that we've been solving. Like, it seems to be much more complicated to actually get down to this O tilde n. So I think that's a very nice open question, and the other one is just this lower bound for approximation, which I've mentioned before. So I think I'll stop here, and thanks for bearing with me.